instrumentation, real time.
I have a shorter
Thank
title.
Ultra low latency AI support to drive.
Okay, so welcome everyone. I would like to tell you a story about how we can improve the operation of detectors with AI support. Yeah, I'm doing this work together with Gregory, who just spoken the previous talk, and also collaborating with researchers from the SLAC National Laboratory. The main idea is very simple. We have somewhere a detector close to, for example, a quantum computer, and we would like to improve its capabilities in error correction or error mitigation or even controlling the quantum hardware by better passes and so on. The main or the most challenging requirement for such an equipment is that here the AI must do its job very quickly, basically on a microsecond scale. And we were working on such solution during the last year. Unfortunately, we couldn't convince any manufacturer of quantum hardware to use or experiment with our solutions, but we have found another good applications for our solution, and this is how we got touch in the guys from SLAC. But first, let me describe the basic idea behind our solution. It is based on the so-called Grok chip, which is used mainly to evaluate machine learning models. It's designed to make it very efficient. Basically, we are talking about a data flow hardware when you need to orchestrate not just the computational graph, but also the data movement. So you need to know always in each clock cycle where your data are situated, and you need to make sure they will arrive at the correct place at the correct time. Because of this, the programming of such hardware is usually harder than a plain CPU, but it comes for an exchange that you don't need to pay an extra time on getting through the cache hierarchy through the CPU-based devices, so you can improve your efficiency. And basically, you can decrease your latency very much. The latency here means the time elapsed between sending the input and receiving the one-shot output. Here, the Grok chip is made of several functional slices responsible for different specific tasks. We have memory between the slices. We have the VXM slice in the middle doing some arithmetic operations, and at the sides we have small units to do matrix multiplications. And from the bottom, we can stream also instructions into this whole setup, which is very nice because comparing to an FPGA where you need to upload a bit stream to the chip and each part of the chip will be fixed in a way what kind of task that particular piece of hardware will do on the chip. Here on the Grok chip, the individual parts on the chip can change their role during the program evaluation, depending on what instruction is coming on streams from down. So it's kind of easier to program. It's more versatile. It sits somewhere between the CPU kind and FPGA kind of programming, bringing the best from both sides. We use this Grok chip in our low latency inference engine in the following way. The main issue, the central issue, is that the Grok chip is deterministic. You need to know what is it doing in each clock cycle. Now imagine how would you interface such a hardware with a CPU-based devices where you don't have this luxury of knowing everything what your hardware does. So we placed an FPGA in between a non-deterministic detector or data server and the Grok chip to take on the role of guiding the data transmission between these two parts and tell the Grok chip when it can start to doing its job, and also stream back the results coming from the Grok chip. The setup of the FPGA architecture is very simple. The main problem with the Grok chip is that it has a very small buffer on the network interface, connected to the network interface. So it's very easy to overflow that buffer. This is why we need basically the FPGA. Basically, it extends the buffer in front of the Grok chip. It can temporarily store much more data and stream the data towards the LPU. The Grok chip is called Language Processing Unit. So it streams the data in a very precisely planned way with a precisely tuned clock cycle frequency and so on. So this is the role of the FPGA, and of course it then transmits back to the inference result to the data server. We got the IP cores for this design from engineers working now at NVIDIA, but formerly they were working at a company called Grok, designing this whole chip, but during the last Christmas they were bought out. So that's the story behind them, very shortly. So this slide is about the specific workflow, how this inference engine works. First of all, you need to turn on, bring up the hardware, and during this process, the Grok card notifies the FPGA how many data it would need to run the evaluation of the AI model. And after that, the FPGA starts to collect the data from the data server. It sits there, it's running, and if data are coming from the data server, then the FPGA accumulates it. And if the required data are gathered, it notifies the Grok chip that, well, you can start your work. So please start fetch data from me. Okay, the Grok card starts doing this, and then do its computation. And after that, it sends back the result of the inference back to the FPGA. And finally, the FPGA sends the data to the data server. The Grok chip also sends, again, a notify message to the FPGA about how many data it will need to the next turn of the inference. Okay, and after that, the cycle starts again. So basically, this is how the whole design works. And by analyzing all of these stages during this process, we realized that bottleneck will be the data transmission between the individual parts. So we also investigated possibilities how to compress the data transmission between the individual components, and we came up with the idea of using this methodology already used in the world of AI by using very small number representation, let's say 8 and 4 bits of floating points. Okay, to implement this, because you need to implement compression and decompression algorithm on both the data server and the Grok chip, because the Grok chip needs to decompress the compressed data it receives. So it's very complicated. when you think about floating point and all of the details around it. So instead of this, we came up with a easier solution just to show that it might work. So this is kind of a proof of concept of using fixed point numbers in this compression. Basically, what we do is that we take the original input data, we shift all the values in the positive regime, so we don't need to bother ourselves with the sign, which would take one bit. And we can make use of all of the 4 and 8 bits of these low number representations. Also, we scale the input data within 0 and 1, and we take the most significant 4 or 8 bits of these numbers, and we send it over the inference engine, bundled together, of course, with the scaling and the offset factor, but those are just 2 numbers. So having a larger amount of data, it would be very, very advantageous to transmit this data in this compressed form. Okay, we have used our method in 2 important applications. One of them is ultra-fast X-ray imaging in some linear accelerator events. I'm not very familiar with the physical background of this process, but the idea is to use a denoiser at the beginning to denoise the raw data, classify whether there are some peaks in the data or not, and then we need to calculate how many peaks we have in the raw data and so on. At the end, the physicist at the accelerator will extract some meaningful conclusions out of these quantities, but for us, this is the part that is the most interesting, because we need to think how we can put this model on the Grok chip. And we could do it. We have measured the latency of the inference with several compression formats. We see that we can position ourselves onto the microsecond timescale, which is nice. But if we compare this inference time to the actual program execution time on the Grok chip, we see that we are spending too much time on I/O. So we started to think how could we improve this, and we came up with a solution by bypassing the servers, the data servers, networking libraries to forge a more specific, more task-oriented implementation to transmit data to the inference engine. And we see that we could improve the latency a lot. Still paying a bit much on the I/O, but we are getting closer and closer to the actual compute time performed on the Grok chip. The second application might be even more interesting. It's about manipulating the plasma inside the tokamak reactor. The guys at D3D had already built a model to help them to keep up the lifetime of the plasma in the reactor, and they could significantly increase this way the lifetime of the plasma, but they are still on the time scale of milliseconds in evaluating their highly compressed model, determining many physical properties of the plasma. And the truth is that the fluctuations of the plasma are on a much smaller time scale than this millisecond. Okay, so they would like to have an inference engine which can operate on a much shorter time scale, and this is where we can step in. We have implemented their model on the Grok chip and performed some numerical measurements how fast we can evaluate their model, and we could already improve to the regime of some microseconds. Comparing to the compute time of the Grok chip, this is still a big time. So we also made a step further using the DPDK kernel bypass library to make our data transmission more efficient, and we can decrease for now, or we could decrease our latency measurements down to 10 microseconds with float 16 and uint8 data compression, which is actually on the time scale relevant to these guys at D3D. So yeah, we just basically finished this experimental development. So what is ahead of us is to test this design in practice and try to improve the operation of the plasma in a real device. So this is what is ahead of us, and I think it's a pretty interesting thing for us. Mostly because some new hardware are also about to released by NVIDIA, which are new versions of the previously mentioned Grok chip with much, better chip manufacturing, much more resources on the chip. They are claiming to release such a server during the fall this year, and we are very, very much keen on how could we use such hardware to further improve our work and potentially even broader the application range of this inference engine. Yeah, just at the end, we have also investigated the numerical accuracy of our inference engine, because being fast is not always enough. You also need to keep the accuracy of your computation. And basically, what we did is that we have compared element to element to a float 32 PyTorch oracle evaluated directly on the CPU server, and it turned out that our accuracy is good enough. So there is no error happening during the transmission. The data integrity is ensured, and also during the mixed precision calculation on the Grok chip, because that's another completely other story, how you can implement such models efficiently on the chip. But let's talk it about another time. Yeah, so what I can say is that we can be both fast and accurate, which is a very nice thing, and we hope we can implement our design in very splendid applications. Okay, so I think this is all. Thank you for your attention, and if you have any question, I would be happy to at least try to answer them.
Okay, thank you very much, Peter. So, question. Oh,
Thank you very much. This is mostly a general question, but what is kind of the way to program the grok chips? Are you writing C++ code yourself, or are there packages to kind of operate these chips? What is kind of the way?
Well, this is a very good and interesting question. I would say that there are no public SDK at this point to program the grok chip. We know how to do it because we have spent around 2 years collaborating with Grok before it was bought out by NVIDIA. The problem is that whatever I would tell you about this, it would be a violation of NDA. so this is I think, yeah, this is my answer to hope you will understand my situation.
I have an even more general question. So you have experience with this hardware, Spectral as FPGA chip, Maxeler, Grok, and so on. So do you have any comment on the sustainability of such systems? So these are very specific systems, no SDK, only very few, very talented or whatever people can do anything with that. So can this move anywhere, or they are always just attempts to do whatever, and it will not work ever, although it would be really, really good and really, really efficient.
In case of the Grok chip, I believe, well, it's a bit stronger than I believe, that there might be designed a programming way of the Grok chip on an equivalent complexity as doing CUDA programming.
Tony?
You mentioned the application of controlling the plasma processes. So what is the accuracy required there? So how you have shown different.
Can you repeat the question?
What is the accuracy required in the plasma controlling process? You have mentioned that you have the int and floating and different things. And is it enough, or is it overkill, or what is the thing?
Okay, these guys at D3D have compressed their model as much as possible, still achieving the predictive power of the model needed for their work. So this is what I have, their model, nothing else. Even to get this model, I needed to absorb several security, entrances into their system. So it's not that easy to answer this question. I don't know much about their internals. I know only that what model they gave us, that model we can reproduce very accurately.
Okay, I think the coffee is waiting for us downstairs. So let's thank Péter again, and also all the speaker of the morning session.